The sliding force isn't really a force per se. It's not a fundamental force, but it's very useful to think of it like one when, say, you're working problems. Let me tell you where it comes from. Suppose you have an object like this that's on an inclined surface. It's on a slope, like a hill or something like that, maybe a car parked on a street in San Francisco, and the hill has a slope of theta like that. So what you might know sort of intuitively is that when objects are on sloped surfaces, they really tend to want to slide down those surfaces. You can think of it a lot of ways, minimizing potential energy, or just common sense. Balls roll downhill and things generally slide down hills. Now I know there might be friction and some other things involved, but just purely speaking, this sliding force has to do with, again, objects wanting to slide down slopes. Okay, so what happens here is that, well, why does it slide down the slope? Well, it turns out if you look at this picture figure here, there's two forces on this object here. The first one is gravity, and we'll label it mg over here, or weight, I should say, not gravity. Weight is pulling down because, of course, the problem takes place near a big planet, on Earth or something. The other force that's acting on the object is the normal force. Why? Because this object here is sitting on an incline, and like we discussed in the normal force here, where this object exists has sort of stressed out this area of the incline, whether it's a street or a table. The molecules here are actually flexing and would like to return back to equilibrium, so the table actually pushes up on the block with a normal force like that. So there are two forces acting on this thing. But now we're talking about the sliding force. Why does it want to slide down the incline? Well, if you look at gravity here, this mg, what would happen if you found the two components of gravity, one parallel and one perpendicular to the incline? So what I want to look for here is it's all about gravity, but I want to find the parallel and perpendicular components. And of course, the parallel and perpendicular are referencing with respect to the incline. Parallel and perpendicular to the incline. All right, well, let's just take a look. Remember that when looking for vector components, the vector is always the hypotenuse of a right triangle. So let's just form a little right triangle here, something like this and like this. And I know if a vector is down like this, one component better be over this way, the other component better be over that way. Those are the two legs. There's your right angle in there, and there we go. And a little bit of simple geometry will definitely prove that if this is angle theta right here, this angle in here is going to be theta also. That's just the way it'll work out. Okay? So what we've done then is nothing really special. This is just gravity, and we have identified the two legs of gravity, or the two components of gravity. Again, here's the parallel one right here. Here's the perpendicular one right here, at least insofar as the incline goes. Now if I get with my trigonometric relations here, and I just sort of find the components, I'll note here that this side is the adjacent side here. So that's going to be mg times the cosine of theta, and this side over here is going to be mg times the sine of theta. This is the adjacent side, that's the opposite side, so I have these two sides labeled. Now let's look carefully. I think we hypothesized very early on when we started here that things tend to want to slide down inclines, so there must be something over here which is pulling down the incline. I'll call that F sub S, the sliding force. This is the one that would want to cause it to slide down the incline, but if you look carefully, this is a force that we're hypothesizing which is downwards and parallel to the incline. And look, here's a component we just found right here, downwards and parallel to the incline. So there's our culprit right there. The sliding force, the force that causes things to want to slide down inclines, is mg times the sine of theta. There it is. This is the sliding force and the conclusion of this particular video here. Whenever something is sitting on an incline, if you know the angle of the incline, the object has a downwards tendency to want to slide down the incline. It's a force that causes it to happen. It's a component of gravity, and it's mg times the sine of theta. That's the force that causes things to want to go down inclines. That's the conclusion of this video, but I have one more thing I'd like to say. In particular, what about the other component here? Well, if you look at the other component over here, that's perpendicular to the incline, but then you're thinking, well, isn't the normal force also perpendicular to the incline? And the answer to that question is yes. And that's exactly another conclusion here, is that for objects on inclines, the normal force of them is mg times the cosine of theta. So this is an example here where the normal force is not equal to mg. The normal force here is not equal to mg the way many students tend to memorize or just sort of hastily write down here. When an object is on an incline, there's two forces on it, gravity and the normal force. The normal force is given by mg cosine theta. And one of the components of gravity, the opposite one, the mg sine theta, is the one that causes the object to want to slide down the incline. That's the sliding force.